So, in this video, I'm going to be explaining the math behind ChatGPT from scratch. So I guess we could start off by asking, what is ChatGPT? And so it's kind of like an overloaded question because essentially, so assume we know what it is, but ChatGPT is an AI model, and it is a model that interprets text to give I'm going to say given output for right now. ChatGPT is an AI model, and it's a model that interprets text to give an output, right? And this output is also text, right? And so we should ask the question further of what is an AI model? What is now an AI model? It's kind of like I hate using the word AI model because AI is a very broad term. We could get more specific if you wanted to know what ChatGPT is, right? So in the realm of AI, I'll make a new text bubble right here. In the realm of AI, or actually, I'm gonna draw. In the realm of AI, imagine this as AI right here. This is AI. That's AI, right? Within AI, you have little small bubbles, right? And so within AI, you have machine learning. This is like very fucking sloppy, but like machine learning. And then within machine learning, you have specific techniques. Like, for example, one is called deep learning. I'll just put deep learning. And so I hate saying AI specifically because of the fact that AI is really AI is just a very broad term. I like to describe it as just like a marketing term. But yeah, sorry, I'm trying to figure out how the fuck to move this shit. Okay. Oh, there we go. Yeah, I like to describe it as a marketing term because in reality, ChatGPT isn't just an AI. It's an AI that is built using machine learning and then using deep learning. And then so obviously you could assume within each little bubble, it's its own little niche thing. So I could kind of break it down one by one, right? So what is an AI model? It is a model that how would I just artificially intelligent, right? It is a model that produces some level of artificial intellect. I'm gonna just say that it is a model, and that's kind of like a redundant statement, but I feel like it still needs to be put down. It's a model that produces some level of artificial intellect. And so, what could this mean, right? I guess we could go in deeper examples like example, right? If else condition, that could be an AI model, right? It produces some level of artificial intelligence by branching out depending on whichever case it's on, right? Scripts, like just simple scripts, like that could be a form of artificial intelligence. This is why I don't like saying AI model. I feel like it's very broad and it doesn't really get to the point of what ChatGPT and other correlated models do in particular, right? And so we could go a little bit deeper, right? So that's AI. Now we know that within AI is machine learning, right? So what is a ML model, right? Well, machine learning model. It is a model, essentially, it's a model that instead of just producing some level of artificial intelligence, it's a model that learns from the data that's given. So, back to what I was saying, what is a machine learning model? So, as we previously were talking about, an AI model is a model that produces some level of artificial intellect. And so this could be if-else conditions, like basic scripts, etc., right? So, what is a machine learning model? How does that differ from an AI model? Well, a machine learning model isn't just a model that learns or that produces some sort of artificial intellect. It is a model that learns from the data it has been given. So what does this mean, right? So if else conditions, they don't learn, they're static, right? In cases of some scripts, they could be static, right? But they produce some sort of intellect because of the branch cases, etc., right? A machine learning model, it's not static. It changes relative to the data that it's training on, right? And so this is important to note. And so, you have many forms of machine learning models, like, example, tree-based models, right? So like, models such as like, light GVM. That was very specific one, but random forest, etc. Those type of models, those are those are like machine learning models because they learn from the data. But then you also have other types of models such as feed forward networks, or I'm gonna say neural network based models. And so this is like feed forward networks, CNNs, RNNs, etc., right? And so we know that a machine learning model is a model that trains or that learns from the data. And then AI is just a general form of some sort of intellect. Now, what is deep learning? So I mentioned here neural network based models, right? Deep learning is essentially those neural network based models. And so we call it deep learning because I don't know how to explain it, but it's just very articulate. Like, so I'm gonna just write it down for clarity. So what is a deep learning, so DL model? I'm gonna low-key spell all these out. Machine learning, and then AI could be the same. So characteristics of a deep learning model. It is a model that is derived from the neural network architecture to learn. There's a model derived from the neural network architecture. Essentially, that's the meaning right there. So like, I said a neural network-based model is a machine learning model, which is true, but deep learning models are the different types of network-based models, right? So it's just like little subcategories, and even machine learning could be branched out into different ones, such as like, supervised, unsupervised, and then reinforcement. But yeah, essentially that's all you need to know right now. And so, we asked the questions: what is ChatGPT? What is an AI model? What is machine learning? And what is deep learning, right? And so from there, I guess we could talk about the most essential deep learning model and what it means. And so let me just draw. Or no. Okay. So deep learning, deep learning, and then increase that shit hella. Okay. Shit, I can't spell. So, deep learning is models based from the neural network architecture. What is a neural network? I guess we should ask that. Or no, what is a neural network? All right. So, oh shit. Neural network. What is a neural network? So, essentially, a neural network is it's a algorithm that's derived from the human brain. And so, if I could get some drawings out. So, in your human brain, like, okay, let's think about how we think, right? So, we think with our brain, obviously, and our brain has neurons. Our neurons store some sort of information and send it to some other neuron, right? And what happens is these firings of neurons essentially create complex patterns that allow us to think and do things that we want to essentially do, essentially creating life. In this case, organic intelligence, right? Or not life, but creating organic intelligence, right? Well, we're working with ones and zeros. This isn't organic. So I guess I could maybe try to find a picture and plop it on here. Neurons. Yeah, like look at that. Neurons, right? Pretty neat, pretty neat. And so the thing is with hold up, let me see if I can find, can I plop it on here? Uploads. Could I do like this? No, never mind. I'm gonna just keep it like that then. Okay. So this is an example of neurons. Network of neurons. What does that look like? Oh shit. Yeah, that's essentially, yeah. That's exactly what it is. I look, he kind of messed with this picture. And so and so yeah, I guess, yeah, this is a network of neurons right here. Network of neurons. I don't know why the font is fucking white. Network of neurons, bro. Nice. And so, network of neurons. Pretty dope. This is exactly what happens in our brains. And I find it really interesting because of the fact that this is essentially, aside from all, the chemicals that are produced and all the other things that happen, this is essentially how a neural network works, right? You have the atom, not the atom, but like think of like the atomic structure called a neuron. So neural network. So what? Yeah, oh shit! Didn't mean to do that. This one's kind of blurry, but fuck it. I think it's, no, this shit's ass. Actually, it's fine. It should be fine. Neural network. Alright. So it's essentially the same thing, right? And this one's like more fucking 3D shit that's in your brain. But imagine this as this 3D projected into 2D. It would look maybe something like this. And so this is a very blurry picture. Sorry. Yeah. So yeah, this is what a neural network is. Essentially, imagine this like idea of like neurons, like a network of neurons in our brain. If we projected it on a 2D space, it would look maybe something like this. Right here, you know. And the idea is this: you want to take in inputs, you want to transform them to give us an output, right? Now there could be one output, there could be multiple. In this case, let's just focus on one output node right here. But yeah, as you can see right here, this is essentially like the same idea. You know, you have the atomic structure, which is a neuron, and this neuron is able to branch its information to the following neurons, and this becomes more of like a recursive thing, such that at the end, the information that's here should be more complex and abstract way. Like, okay, so think of it like this, right? Imagine these as taking in some sort of basic structure of some sort of function, right? Over iterations of them going up the layers, so from this layer to this one, the information that was derived from here, which was basic, should transform to a more meaningful interpretation of the original information, right? So think of it more or less kind of like it's building upon the facts of the previous layer to give a more fuller image of what's actually going on within the function or whatever you're trying to predict, right? So imagine this was like you're trying to predict, let me see. Okay, I could give the example of like an image. So yeah, let's just do that. So imagine this input layer. I know there's only 3 nodes, but imagine them as being like, if you have an image like 32 by 32 or whatever, like that many nodes, right? So this beginning layer would only abstract each pixel, right? It would only have the information of an individual pixel. And so when it goes to the next layer, since these other nodes are interpreting every other, like the sum of every pixel in the previous node, it's now going to take that level of interpretation to a higher level. So instead of just interpreting a pixel now, it's going to be interpreting maybe whole strips, maybe like the whole image as a whole, right? And then, you know, it keeps going on the layers, and from strips, it might encode like, you know, shapes. From shapes, it might encode like animals or some sort of structure, more complicated structure, and eventually at the end, it'll produce you what the hell you want, right? That's the core idea of a neural network. It just learns, like, as you go through the layers, the complexity of the patterns it's able to interpret increases. And so why is this? So what is a neural network at the end of the day, right? And so why is it able to do this? So again, a neural network is just layer of neurons. But if you have layers of something, what does that make it essentially? Well, if we look right here, there is the input layer. We have hidden layers, And then we also have the output layer. Okay, so, and I'm gonna kind of break this down one by one, just so everyone can get a clear understanding. But input layer, there's only one input layer. Now there could be multiple inputs into the input layer, but there's only one input layer. Makes sense, right? Output layer, there's only one output layer. You can only have one output layer, but you can have multiple outputs. Same thing. Now hidden layers, these are the things in between the output and the input and the output, allowing the information to transform throughout the layers, right? So this uses, a decent amount of, little bit of complex math, but I'll be explaining it shortly. So we talk about the input layer. So how is information able to transform, right? So, a lot of the times when we think of input layers or inputs, we think of them as like 1D, 2D graphs, right? So if I was to take a tool and start drawing, like if you, or like, actually do textbooks. Yeah, like when your teacher used to be like, oh, y equals 2x, right? I mean, the input is x, the output is y, right? And so it's linear, or just you know what it's going to be following the next one, right? And so naturally we have this idea that the variable itself, the variable is one-dimensional. Well, in neural networks, it's not necessarily one-dimensional. When we think of a variable, or when we think of something, we don't think of it as the atomic structure of a neuron. We think of it as a layer as a whole, right? Because think about it, they're all going in parallel. They're all transforming at the same time, from one layer to the next, the next to the next, to the output, right? So thus, we could think of it from more of a linear algebra point of view, instead of we having to think of, okay, we got to do this one node, then here, and then this one node. We could think of it like this. Okay, we could do these vectors, aka this layer of nodes, and this layer or vector is transformed by some sort of matrix to this layer, which then is transformed to this layer, and so forth, right? And so that's when we start to get to the linear algebra approach. Linear algebra. So a input, so I should say it like this actually. A input or input layer is essentially just a vector of and that makes sense, right? And the explanation I gave, think of each neuron as taking up a little slot within a vector. So I could maybe draw it out right here. And so, you have, I'm gonna do, this is supposed to be an N, by the way. And then like a subscript 0, subscript 1, and subscript 2, right? This is essentially what I'm talking about. It's a vector of inputs, right? Now I said N, but it probably would have been more clear if I said I, but this is like a general interpretation. You could think of it, a vector of inputs. And so, all right. So you might be wondering, okay, how the hell could you transform this into this? Now, this is where the linear algebra approach comes in, right? Now, as you can see, there's connections. Now, I'm going to reference back to the network of neurons, right? So in our brain, we have neurons, etc., blah, blah, blah. So these neurons learn over time, through some sort of event. And so they might have connections to neurons that they might initially have, but over time they might try to diminish that connection through some learned event. Or it could be the opposite, where they might try to increase a connection through a learned event, right? And so you could think of these kind of like weights, right? As the model learns, as the brain learns, the weights between this neuron to every other neuron it's connecting to, it could either increase or decrease in respect to that other neuron, right? Same thing happens here. See these lines, these are edges, but these edges carry a weight. And so the weight could either grow or it could shrink. It grows or shrinks relative to the data, right? So let's just say this edge was connected here, but we notice that with this connection here, it caused a massive skew and bias towards a specific term, right? Then with that, with us realizing that, we would try to reduce the weight between this edge and this edge such that these other edges get a chance to express their novelty, right? And so this is important. Later on, I'll explain a little bit more why, but yeah, this is very important. And so essentially what I'm saying is you need some sort of way to transform this vector into this, this right here. And so that's when we start to get into, okay, we want a matrix of weights, right? So if we do this, so I think it's like it would take me a long time to draw all of them. But essentially, it's gonna take me forever. Yeah, something like this. So, boom, 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 boom. So this is a So imagine these are subscripts as well. I just don't want to fixate too much on them. So this is a matrix of weights, and so as you can see, the length of this, or the length of this column of this vector is 3, and so the row, the length of this row of this matrix is 3. And so, I mean, with the understanding of linear algebra, you would know that these would cancel out, and then it would result in a new matrix of or vector of size 4. Correct me if I'm wrong. I know it's essentially you're multiplying this input or vectors by a specific matrix of weights, and thus it transforms the input of vectors from this to something like this. You know? So yeah, something like that. This, so input layer times weights that connect to the next layer gives you how many neurons are in the next layer. Essentially, this should make sense. You know, I'm omitting a lot of little niche things, but I just want to save time. But yeah, what else? Okay. So that's essentially how it works. Now I find this interesting. Why? So if we look right here, you know, you notice this is a 3-dimensional vector, right? This three-dimensional vector is being scaled by some sort of matrix or transformed by a matrix to produce a four-dimensional one. And so this was kind of what I was referencing in a sense. So within neural networks, data could transform. It transforms all the time. Not only does it transform in dimensions, it can transform in other ways that we'll see further. But yeah, the weight is a form of it's a way of transforming the data. The idea of, scaling the data into new dimensions is a way of transforming. Yeah, there's other ways that will get you further. But, it's a layer of input vectors, and so these inputs can transform into higher or lower dimensions. So yeah, these inputs could transform into higher or lower dimensions. It's just relative to whichever architecture you pick. So this kind of touches on something called a hyperparameter. You're able to choose how big or how small you want your architecture to be. So generally speaking, it's like a manual thing. There are some techniques to make it automated. I can maybe touch on that in another series because that's kind of out of scope, but yeah. So let me talk about output layers, or hidden layers. So with hidden layers, I'm going to go a little bit more on depth. So yes, this is essentially the model of how it works, but I'm omitting one key detail. It doesn't just multiply weights to a neuron, it adds some sort of thing called a bias, right? And so a bias is layer wide. So a bias is added here. So essentially, the dot product between this input vector and the weights happen, right? But after that dot product, you're going to have an addition of something called the bias vectors, right? So boom, boom, boom. Yeah, I think something like boom. Something like this. So I'm not going crazy in detail, but just understand these are used to transform a neuron, right? The bias, think of it like a simpler way of understanding it is just going back to like middle school algebra. Y equals mx plus b, right? We have the m. What is the m? It controls the slope. By how much does something change, right? What is a b? It changes the y-intercept. Like, where is the starting point? Think of this essentially as the same thing as this, right? It's the same thing, but just higher level. You could think of it like y wx plus b. Weight times x, so weight matrix times x vectors plus b vector, bias vector, right? And it gives you a y vector. Essentially, it's the same thing, literally the same thing, if you ever wanted to know why, right? Now, additionally, these are cool, but there's one thing you want to know, right? These are essentially just linear transformations by themselves. The idea of scaling something and moving it, so translating it with B, scaling it with W, scaling / rotation with W, that's essentially, it's still a linear transformation, right? It becomes difficult to derive meaningful patterns when all you're doing is changing up, like all you're doing is just scaling and squashing the shape that you're manipulating it within. So like, let's just imagine I had like a square, right? If I had a square, what is essentially happening when I'm doing this? Because mind you, this is you could think of this as a plane. You know, this is a plane and it's being transformed by the weight and it's being translated by the biases, right? So what happens? Well, okay, no, that's not what I want. Let's see if I can unlock this. I don't know how I'm able to move this. Okay, so essentially think of it like this. All I'm able to do is I'm able to move it with B. I'm able to scale with W. I'm also able to rotate. That's not how you rotate. Yeah, imagine me being able to rotate. Oh shit, rotate, right? That's all I'm able to do. That's not what, like, that's not the most optimal thing I'd want, right? Because let's just say I had started off with a square, but the data I had was in the shape of like a, say, triangle, right? Now, it's cool that I'm able to scale it, like I'm able to scale, I'm able to rotate, and I'm able to translate, but at what point am I able to fit the data, like the weights and neurons to the data I'm training it on, right? I could only ever approximate it, never really truly fit. And so this is where you have something called nonlinearity, where you don't just transform something based off of just linear transformations. You transform it based off of whatever the hell. Like, essentially, it's like I'm trying to say with nonlinearity, you're able to literally imagine you compressing these two ends, and now this square could compress itself to a triangle and then thus fit onto the data, right? That's a property of nonlinearity. And so this is really important in machine learning because of what I just explained. Patterns could be limited because of the starting shape of whichever data the function, or whichever the function is on. You get what I'm saying? So nonlinearity allows you to scale the plane non-linearly of which the model lives on. This is really important. And so let's add even more data that I omitted. So if I move this a little bit further as well, imagine this now having something. I'm gonna draw it like this. This is typically how it's drawn. So boom. So what is this right here? It's supposed to be like a Greek symbol, but it looks like a fucking apple. But essentially this is supposed to represent all of this is being transformed by a nonlinear function. And so what is a nonlinear function? It's a function that isn't linear. But what the fuck does that even mean? So you have two that people mainly use. So I'm gonna reference sigmoid, which is best understood. And so it's a function right here. It's not a straight line, right? It's not linear. It doesn't go up for every increase in x, it doesn't increase y per se the same amount. And so, think of this as a way of it's just a way of allowing the model to express based off of what the input is, but such that it doesn't scale the expression linear to the past inputs that were put in to express that. That didn't make sense, but I explained it in my past examples, so essentially I'm referencing the same thing. And so these are used to basically kind of think of it as a way of not only controlling how much something increases, but also allowing the increase to make a slight little fold in the function that the model is trying to represent at that point in time. So given the square example, wherever it is, the model is trying to make a little slight fold um, on the square, such that it represents a little bit more like a triangle, right? And so um, this is a sigmoid function. That's typically one of the activation functions, but the most used one is something called ReLU. And so essentially, it's a function that is 0, everything below, for all inputs below 0, and it's x for all inputs above x, or above 0. So essentially, it's like, okay, if the input is negative, just treat it as 0. But if the input is anything above 0, treat it as that said input. And so this is nonlinear because of the fact that think of this function as a way of making slight little folds in the data, right? If you have any points that are negative, it's just going to fold all that to positive, or into being 0, negative, or 0. This is kind of shown through the function itself too, right? So essentially think of this as if this was originally a linear function, right? Like y equals x or whatever the slope is, you would think of it going increasingly down, but this function is shown best through understanding itself by making a fold in itself, such that anything below 0 is still 0, right? That's the output. And so this is important because, like I previously mentioned, it allows you to make folds in the data, right? It allows you to fold the expression of the model. And continuous folds result in a more accurate precision on the data as a whole, which was shown through the square triangle example. And so essentially that's what the hidden layers do as well. I'm gonna just say it like the input layers, input to hidden, that's what they do, and then so forth as well. Okay. Layer is transformed by a non-linear function to obtain the expression of the model. And so, this makes sense. I like to think of this like more on a philosophical level, right? Or I guess you could say logical. Let's just say I showed you a picture of like a cat, right? Now, if we were to think linearly, we'd just be like, okay, this is a cat. It's a cat. It's a brown cat. Just nothing beyond the fact that it's a cat. But to think non-linearly, it's to be like, okay, this is a cat, but why is this a cat? Why is this here? What is the setting? What I'm saying? It transforms. Your thoughts transform over time. And so that's one of the properties of nonlinearity, the ability to transform outside of the original function of expression. Exactly. So I think it's pretty cool. And then final layer, output layer, essentially it's just like the input one, but all the math still applies, but this is where you get the output of your network. So this is where you get the output of your network, right? In this case, it's one neuron, but many other cases it can be multiple. There's different ways depending on what you're doing, but and so this is what a neural network is, math behind it. I guess maybe I could stretch this to a part 2 because of the fact it's kind of stretched a little bit long. But this is essentially the foundation of what a neural network is. I find it really interesting. You go a little bit more theory behind it. So how I like to understand it, each neuron holds information. That information is transformed throughout the layers, right? And so there's a correlation It's like not as obvious as it may seem, or maybe obvious, but there's a correlation between information and transformation, right? As you maintain more information throughout the network, the transformation is decreases, right? Or there's probably like little bits of transformation. So, for example, what I'm trying to get at is as you retain the information of the original input layer, and it's like still being able to be propagated back here, the transformation of that said input is decreased or is low in a sense. I could better explain this through showing like, the telephone game or some shit, right? You have person A that says something to person B, and that person says something to person C. And so I'm sure you guys played the telephone game before. It doesn't end well, right? Why? Because the information that was first passed in has been transformed, right? So, let's just say I have a cat, and it could then transform to be sorry, holy shit. How the hell do you fucking move this shit? Okay. I have a bat or some shit, right? To, I don't know, like fucking rat-a-tat-tat or rat-a-tat bat. Like, what the fuck? But just example, right? You had original information, but as that information transformed over time, it became something almost unrecognizable of the input. And there's pros and cons between this, but essentially this is what a neural network does. It takes in input and the information of the input, and it transforms it to something more meaningful. So imagine if this input was just rat-a-tat, bat, and then maybe let's just say it was the other way around, right? We could actually say a neural network works the opposite of the telephone game. The goal is, instead of the information degrading over time, we're getting more valuable insight from that said information that might just be mid, right? So let's just say from A we had rat-a-tat bat, but then to B we had I have a bat, and then finally at C we say I have a cat, which let's just say was the original interpretation of whatever this is, but there was maybe so much noise in the input data that we couldn't really interpret that as humans. Right? So essentially, this is what I mean between the correlation between information and transformation. And this is something I kind of learned on my own. Information versus trans. And so, to gain a deeper insight, neural networks are battling between the balance of information and transformation. Yes, as you maintain more information, so maintaining information would just be like, instead of it having I have a bat, it'd just be the same shit every single time. It maintained its information, right? So this is what it means to maintain information. This is bad in this case. Why? Because the original information was noisy, right? I mean, let's just say in the case where it wasn't noisy, like I have a cat. Yeah, it would be best. Like, it would be good, right? Because you want to, like, it wouldn't be bad. It wouldn't hurt to keep the information. But through keeping information, you lack the transformation that comes from the lack of information, right? Or the diminishing amount of information. So I'm gonna talk more about this maybe later on, because this touches on something called information theory, which I actually find really interesting. But yeah, essentially this is how I'm gonna wrap this up. But essentially this is part one of how ChatGPT works. More specifically, what is a neural network? How does that work? and I added a little bit of my own 2 cents of the balance between information and transformation. If you have any questions or comments, let me know below in the comments below. Other than that, thank you all for listening. Have a great rest of your day. I don't know.